Thanks. It's been a real pleasure to be here so far. It's always fun to be at a conference about something that I don't know anything about, because then I can just pay attention to the ideas and not have to worry about understanding all the details. So now it's your turn. The title of my talk is a question, and to be honest about it, if you asked me to bet on this right now, my answer would be probably no, that probably quantum gravity, we can't learn very much about quantum gravity this way, but we might be lucky. The basic problem is that gravity is weak. If, for example, you think about an interferometry experiment and you ask what the gravitational effect of a component going through one slit is on the component going through another slit, you just put in some numbers and you immediately get a factor of 10 to the minus 48. Times some other parameters which you can fool with a little bit. You can take a big mass, you can take a slow velocity, you can have a long interferometer with narrow slits, but it's awfully hard to get 48 orders of magnitude up. People can, of course, do gravity experiments with interferometry, but that's by using a very large mass here instead of looking at two particles going through an interferometer, a particle going through an interferometer. Sorry, I'm afraid this is going to keep doing that. No, maybe.
Connection's not stable.
Okay, is there a plug here? Yeah, okay, let me quickly do that then.
Yeah, that may be it.
Yeah. I set it for good efficiency and not much energy saver, but that may have been when it was plugged in. So, okay, let's try again. Okay, it's already brighter. So you can do gravity experiments with interferometry, but that's by using a mass which is something like a reservoir full of water. Well, a neutron and some other mass, though, and the Earth, say. So,
that tends to work.
Yes, but the Earth, but it's hard to do interferometry with the Earth as itself. And those are, in some sense, classical experiments. It's looking at quantum effects, but with classical gravity. When you get to quantum gravity, you have another characteristic scale, the Planck length, 10 to the minus 35 meters. So it starts to look really impossible. But we might get lucky. There are a couple of ideas floating around that I'm going to talk about. One which I am not an expert on, but which hasn't been mentioned otherwise in this conference, and I think deserves a brief discussion at least, is testing modified dispersion relations with cold atoms. And the second, which is something that I have worked on and is much more speculative, is testing whether it's possible that gravity is not quantized using molecular interferometry. So let me start with the first. Basic idea is that the ordinary dispersion relations that we use all the time come from the Poincare group. And when you add gravity, the Poincare group is no longer exact. And if you add quantum gravity, there are various things that might happen. One thing that might happen is that the group may be deformed to a quantum group, for example. This happens naturally in many models of non-commutative geometry where spatial positions don't commute. And that's not such a strange idea in quantum gravity theory, since measuring the x position requires using a measuring apparatus which has some mass which distorts the metric in the y and z directions. It also comes naturally in a set of models called doubly special relativity, which are attempts to modify Lorentz transformations so as well as having an absolute velocity, an absolute speed, there's also an absolute mass, the Planck mass. A second possibility is that quantum gravitational effects could simply break Lorentz invariance at the Planck scale. And again, this is not such a strange thing to expect. For example, if there's any kind of discrete structure at the Planck scale, it's very hard, although not impossible, to maintain local Lorentz invariance. Or another interesting possibility, which is one of the things I'm working on now, is that there's some evidence of an effective dimensional reduction of space-time from 4 dimensions to 2 at the Planck scale. If something like that happens, that would also break Lorentz invariance. So in either case, you expect modifications of the dispersion relations. And deformed dispersion relations typically look something like this. You get some nonlinear effect. This is, say, an energy, an initial energy of an atom and a photon. And for your conservation, you get additional quadratic terms. For breaking of Lorentz invariance at low energies, you expect possible terms proportional to momentum and momentum squared. So can you see these? The basic idea is to use 2-photon Raman transitions, which I expect that most of you know much more about than I do. But from my fairly simplistic theorist's approach, what you're really doing implicitly is measuring conservation of energy and momentum and addition of energy and momentum, where the picture is you have some photon coming in, exciting an atom, photon going out, de-exciting, and you basically just use conventional conservation of energy and conservation of momentum to obtain the expected value, for example, of h over m, which you can then measure. If you deform either the addition of energy, which deformed dispersion relations do, or if you break Lorentz invariance, then this step, these 2 steps are going to change. So for example, with deformed dispersion relations of the type that I showed on the last slide, the energy that you get over here is no longer just h delta nu, it's h delta nu times 1 plus this extra factor, which parameterized the quadratic terms in the dispersion relations, the extra quadratic terms. So now you do the experiments that, again, I assume you know better than I do with cold atom interferometry. And the current limits for deformed dispersion relations are that this factor kappa has to be less than about 7 or 8 orders of magnitude larger than the, or smaller than the Planck energy. That is not yet at an interesting regime to test quantum gravity, probably, although there are models where gravity gets strong at much lower energies. But if the experiments can be pushed another 3 orders of magnitude in sensitivity, you start to probe reasonable predictions of some of these non-commutative geometry models. For direct Lorentz invariance breaking, the current limits on this linear term on C1 are fairly small, I think 10 to the minus 5 or 10 to the minus 6, which means that, that you would have to have some unusual fine-tuning in a quantum theory of gravity that predicted a piece of the dispersion relation like that. Unfortunately, that's probably not what most theories would lead us to expect. Most theories would start with a p-squared term. And there, again, the limits are not yet at the the level that you can test reasonable quantum gravity models, but they're within 3 or 4 orders of magnitude, I think. So there may be something interesting here in the not too distant future. I think I can say that given the incredible progress that I've seen in the experiments recently. So that's one area of testing. But now let me go on to the second, which is an area that I've worked on and probably is the thing that got me invited to this conference. And that is testing the possibility that maybe gravity simply isn't quantized. Now, normally, many physicists, certainly elementary particle physicists and relativists, will hear that and cringe and say, well, everything is quantized. Why should gravity be different? On the other hand, gravity is different. I mean, in our standard description, most interactions take place in space-time, and gravity is a description of space-time itself. So maybe gravity just doesn't fit in with everything else. Now, there are some standard hand-waving arguments against this that basically say if you have any non-quantized field, then you can use that to make measurements and violate the uncertainty principles. And I think the people who have worked the hardest to make that precise for gravity are Epley and Hanna, who published a famous paper, well, famous in a small circle, paper in 1977, in which they argued that depending on your view of whether a gravitational measurement causes a collapse of the wave function or not, that having non-quantum gravity coupled to quantized matter either gives you non-conservation of momentum from violations of the uncertainty principle, or else lets you signal faster than light by allowing you to detect a collapse of a wave function instantaneously through a gravitational measurement. But there's a fair amount of hand-waving that goes into these arguments. There are a lot of loopholes. The conclusions depend on particular guesses as to what non-quantum gravity would look like, particular interpretations of quantum mechanics. If you look at actually setting up an experimental apparatus to make one of these problem measurements that Epley and Hanna talk about, you often find that it requires concentrating enough matter into a small enough region that your apparatus collapses into a black hole. And possibly that could be made systematic. If there is momentum non-conservation, it's not clear that it's large enough to measure. I mean, and if it is, well, that's an experiment to go to. There's a quote by Rosenfeld, who used this kind of thought experiment to show that electrodynamics had to be quantized, and was asked, well, what about gravity? And basically said, well, it's nice to have quantum field theory, but remember it was developed for particular circumstances, and you can't just blindly extrapolate beyond those circumstances. He ends saying, even the legendary Chicago machine cannot deliver the sausages if it's not supplied with hogs. Excuse me. So at the bottom, this ought to be an experimental question and not just something for theorists to debate with each other about. But to make it into an experimental question, sorry, bad allergies, you have to ask at least something about what non-quantum theory of gravity would look like, what the field equations would be. So if you simply write down the Einstein field equations, you have something that doesn't make sense. It equates a C number, the Einstein tensor that describes the gravitational field, with an operator, a stress energy tensor built out of quantum fields. And that just, it's mathematically meaningless. You can try to interpret this as an eigenfunction, eigenvalue equation, but then you run into trouble because not all of the components of the stress energy tensor commute with each other. So in general, they won't have simultaneous eigenvalues. So what you really need to do, if you're not going to make an operator out of the left-hand side, you have to make a C number out of the right-hand side. And that basically, in ordinary quantum mechanics, means sandwiching the energy tensor between two states. The simplest way to do that is to just take an expectation value. This leads to a model called semiclassical gravity that was proposed independently by Muller and Rosenfeld in 1962. As Kibble and Ranjvardhemi first pointed out, I think, if you look at this a little carefully, you realize that even though it's just supposed to be a theory of gravity, it actually has drastic effects for quantum mechanics. It makes the Schrodinger equation nonlinear because the metric, or the space-time geometry, is determined by a state, which gives you the expectation value, but the state obeys a Schrodinger-like equation in a curved space-time in that metric. So there's a feedback, and quantum mechanics itself becomes nonlinear. Now, if you want to do experimental tests of this, it's not a matter of looking at Mercury's perihelion or the deflection of light or anything like this. This is an effect of ordinary low energy, low velocity, weak field gravity. And so it ought to be fine to just look at the Newtonian approximation. The Newtonian approximation of this is the Schrodinger-Newton equation, which is just the ordinary Schrodinger equation with a potential, which is the gravitational potential, but in which the source of the gravitational potential is the probability distribution of mass rather than some point distribution. So this is the equivalent of taking an expectation value over here, and then this is the Schrodinger equation in that background. The probability interpretation is still valid, even though this is a nonlinear Schrodinger equation. You have a conserved probability density, you have a probability current, and all that. There are no immediate deep questions about interpretation, except about what a measurement means and what happens if you collapse the wave function and all that. That I'm just going to avoid. I have no idea. The stationary solutions of this have been investigated for a while. It's known that there's a stable ground state with a tiny, tiny mass. MP here is the Planck mass. So if you're looking at a ground state for a hydrogen atom, this is 10 to the minus 76 times the mass of the hydrogen atom. So the ground state energy is very nearly zero. It's known that there are excited states, but they're not stable. But what really is interesting to understand is the dynamics, and very little is known about that. So what my student Peter Saltzman and I decided to look at was the simplest possible question, which is just starting with a Gaussian spherically symmetric wave packet, let it evolve and see what happens. Now, it looks as if there are a bunch of parameters in this equation, but there's an overall scaling. So in the end, you end up with a one-parameter family of solutions. And for example, you can fix the width of the wave packet and then vary the mass and cover the whole space of solutions. Now, this is not an easy problem because it involves a large separation of scales. If you look at a typical size of the gravitational term in the Schrödinger-Newton equation and compare it to a typical size of the ordinary kinetic energy term, for a mass of, say, 10 to the third atomic units and a typical size of a micron, you find that those two terms, the ratio of those two terms is 10 to the minus 19th. Gravity is very weak. On the other hand, the equation is also very nonlinear. And the nonlinearities, we think, turn out to make a large difference. So what we did was to just arbitrarily pick a width and solve numerically for a range of masses. Now let me do a little hand waving about what you might expect to happen here. The picture is that you start with a Gaussian wave packet. You know that if it's just a free particle, it'll spread. But there is a counteracting force here because in this semiclassical or this non-quantum gravity, the wave packet self-gravitates. The distribution of probabilities gives you a distribution of expectation values of mass or a distribution of mass. It acts like a massive sphere. Gravity tends to make it collapse. If you do some simple hand waving, you can say, well, let's just look at the ordinary spread of the peak of the wave function without gravity, take the second derivative of that, and set that equal to the gravitational acceleration to see when they balance. And if you do this at time equals 0, you find that they balance for a mass which is given in terms of Planck's constant and Newton's constant, which is large, but has this nice power of 1/3 in it, which makes it not nearly as large as you might have guessed from looking at the equations initially. For a width of a micron, this hand waving gives you this start of collapse for a mass of 10 to the 10th atomic units, which seems too large for now.
The 1/3 just comes from the fact that it's a spherical.
No, it's because there's a 1 over m squared here and there's an m there. It's just the mass dependence of the two processes. So this still looks way out of range of experiments, although I understand people are talking about doing some pretty remarkable things in the not too distant future. But this is certainly an underestimate for a couple of reasons. One is that the spreading, if you look at the time dependence, the spreading acceleration slows down faster than the gravitational attraction. So even if the thing doesn't immediately collapse, it might collapse later. And for reasonable times, that can give you an order of magnitude or two. And the second is that the process is very nonlinear. And so this shouldn't really be trusted. So what we did was to do the simulation, and we found 5 different phases. Now, these masses are all for the initial width that we stuck in and have to get rescaled depending on what particular experiment you're looking at. But what we found is that for small masses, you get behavior that's indistinguishable from a free particle, at least at our level of precision. For somewhat larger masses, you still get a spreading of the wave function, but it slows down, as you would expect from this physical argument. For a relatively small range of masses, you get some very complex behavior in which the spherical wave function basically spits off little shells that go out to infinity. And that, it turns out, was also known from looking at the behavior of some of the stationary solutions, which looked as if they had shells, and you knew that if you perturbed them, the shells would start to head off to infinity. For somewhat higher masses, you get a collapse, gravitational collapse of the wave function, rapid shrinking of width. And then for high enough masses, our simulation just couldn't run long enough to tell what happens. So here's an example of what I mean by complex behavior. The pluses here are the wave function with the gravitational interaction turned on. The green is the corresponding wave function with no gravitational interaction, just free particle. And here is an example of collapse, where the green is no gravitational interaction, and the pluses are with the gravitational action turned on. And here is a sort of a phase diagram of our results. The interesting phase is this phase C, where the wave function collapses, because that's potentially detectable. That means that you would expect interference to disappear. And as you can see, this is that's the, I don't know if you can read that, that's the log of the mass in atomic units, and this is the log of the width in microns. And so if you go up to a large enough width, you can go down to a fairly small mass. So, I mean, here are some numbers. By themselves, they don't mean a huge amount. But what's important here, this gives the range of masses, the range of masses and widths for which we get this gravitational collapse behavior. And you can see that it's not that unreasonable at the low end. And in fact, if you take the fluorofullerene atomic interference experiments and stick them in here, you find that you're somewhere near the edge of our collapse region. Now, unfortunately, that life is not quite that simple. For one thing, the wave functions there are not spherical. You have to do some compensation for the fact that the wave functions coming through these collimators have some coherence length that is longer than just the width, the vertical or horizontal width of the wave function. The profile is certainly not Gaussian. So our best estimates are that we're away from this collapse region, but by a factor of maybe 500 or so. So what's next? Well, first of all, the first question is whether you should believe these computer simulations. And the answer is that I'm not quite sure. It's not that easy to do a simulation in which you have two terms that differ by a factor of 10 to the 12th and their coefficients. We are waiting, but there's another group that promised to check our calculations, but we've been waiting a long time and haven't yet heard from them. So if any of you have good students who want to do a fun computer project for a while, this is certainly worth redoing. And then presumably it's not that much harder to do with different profiles to look at some cylindrically symmetric but non-spherically symmetric wave packet, for instance, to start testing the sensitivity. For experiments, the big things that would bring the experiments closer to our suggested interesting range are heavier molecules and narrower wave packets, both of which, I mean, it's sort of obvious that if in either case you expect more self-gravitation, and so more likely and a quicker gravitational collapse. But if this can be done, then it's possible that we could test at least this simplest model of non-quantum gravity and perhaps have experimental evidence that gravity really is quantized, or that it isn't, in which case we'll spend years looking for other reasons for the interference to have disappeared. Okay, thank you.
Questions?
We know that one graviton exchange, the work of Feynman and others, reproduces classical general relativity. Imagine having a theory where you didn't quantize gravity and trying to calculate higher order corrections. I mean, what picture would you have of trying to do that in the first place?
If you didn't,
I mean, if you couldn't
okay.
if you accept the idea that gravity isn't quantized, how would you imagine doing even a simple calculation, radiate corrections to one graviton exchange or whatever to go beyond what we already know?
Well, if gravity isn't quantized, then you probably don't want to use a description of one graviton exchange as your description of classical gravity.
So even though that works, you would throw that out?
Yeah.
No
I mean,
gravitons.
the one graviton exchange is, in some sense, the classical limit of the quantum theory. And so...
It works, you're willing to throw that out anyway. That's fine.
Yeah, I mean,
that's fine. Right.
Yeah, I'm not hoping for this. I'm not hoping for this, but I mean, that would put me out of business, right? But I'm saying you have to think of it as a possibility.
Well, I very much like the idea of a non-quantum approach to gravity, and maybe that it's connected to the geometry of space-time. And a question that I have is to be looking at how one might test such a theory on the basis of let's say, interferometry. So physicists are very good at measuring phases, but they're also very good at measuring, maybe even best, measuring frequencies. How likely is it, or is there even a theory, where you go back to your slide which you show the Newton, not Newton, but the
Schrödinger-Newton.
The Schrödinger gravity theory.
Schrödinger-Newton is...
Yeah, and I'm wondering this, is if you were, has somebody extended that to see how, make it not a Schrödinger, but say Schrödinger-Pauli theory, we've got spin, or to full Dirac kind of theory, and then see what you predict for the hydrogen hyperfine spectrum, because the hyperfine spectrum can be measured to 1 part in 10 to the, I don't know, 14th or 15th by now, and if there was a slight discrepancy, maybe you would do it, or maybe gravity would be instrumental in giving us some kind of a handle at a level where physicists actually are now capable of measuring such a discrepancy.
That's an interesting question. There's certainly nothing hard about doing that in principle, and I don't know offhand if anyone has. I know that the ordinary gravitational corrections, the quantum gravitational corrections to hydrogen hyperfine structure are still quite far beyond the reach of experiment. But I guess Charles Wang is not here, or? Okay, because he has an interesting paper about gravitational Lamb shifts in Bose-Einstein condensates, which is getting at that same kind of issue. I don't know whether to believe it or not. I wish that he had been here.
Well, you mentioned experiments with a certain mass, right? But we've also seen a talk from Professor Baumeister with even much heavier objects. Have you really looked into those numbers to see what that would do for your predictions?
I have not. I mean, certainly for an individual, well, I've only looked at single particles, but I mean, just looking at a single mirror, whether you can expect a quantum superposition, I'll have to think about that. There is this recent result that he talked about of a superposition of states of a resonator that might already be enough to do something here.
Okay, if there's no other questions, then let's thank our speaker again.